I put you out on 4 spots on that outcrop where that was intersecting that surface. I put somebody down in the bottom of the gully. I put somebody over here who was moving around, I guess, or no, this was the, yeah, that's right. This person moved around. There was a person over here, and there was a person over here, right? Now, what did I do? I had this person move around till they were at the same height as this person, right? And you put a spot on the map. That meant that you were at the same position in space. If you were to draw, and you measured the azimuth, you used your compass to measure the azimuth of that line. That line is a strike, right? But the strike is also, because this is equal elevation along this plane, this is a structure contour, is often referred to as a structure contour on the plane. There are an infinite number of these lines, right? That all represent structure contours on the surface of that particular plane. What we're going to do now is turn this around the other way. That was an illustration where you could just do that directly in the field. That's kind of ridiculous because in the field you can just make a measurement. You don't have to do that. But what if you're in the scenario where I don't really know, I can't see that map trace. And instead, all I know is I can find that contact here, here, and here. How am I going to find that? Or how am I going to find that point or this other point? And how am I going to figure out, how am I going to exploit that to figure out the strike and dip? Well, you can do that by a thing called the 3-point problem. And I'll illustrate it here. Same issue. I'm going to go back to a blank piece of paper. They like my visual aids. So.
Yeah, it's pretty creative.
Here at the last minute, I didn't think about. I meant to do like a
that's even devolving from your overhead projector style.
Definitely devolving. I should really lay it here, right? Now I'm on a horizontal surface. Let's say what I really find. Now remember, a map view is looking down on something. So I'm projecting everything up or down to a horizontal surface. And I find somewhere on this surface, I find a point there, I find a point there, and I find a point there. I have enough information here. I got a triangle. That represents 3 points on that surface. If I just have 2, I can't determine the orientation of this plane. It could be anywhere around that pair of lines, right? I could rotate around that pair of lines or that pair of lines. But the moment I have 3 points on the inclined plane, I have enough information that I can figure out the orientation of the plane. How do I do that? Well, one way to do it is, here I can tell you, you can see what it is here. It's like your experiment, right? If I could find the horizontal position, that's this position over in here, I can find the strike line like we did in the field. But how am I going to do that? Well, turns out, a very easy way actually. And maybe this is a triangle, right? There are proportions here. If you think about that distance, there are relationships between this distance and vertical distances. Let me say that a different way. Let me just show this a different way. I'm going to put it on the board now. Think about that triangle I just drew. Here's a high point, a low point, and I'm going to put an intermediate point. See if I can say this a different way. I'm actually, let me put a number on it. Say this is 1,000. This is 0. And this is 500. This is the lowest point. This is halfway up to that position, and this is 1,000 feet or whatever units you may have. In fact, maybe I should draw that on here instead of that.
And you're going to use the measurement that's exposed at both the high and low, right?
Yep. I would have to draw this properly here. I might do it here. For my particular case, I'll draw it here again. This is a little simplified, but won't matter for now. Here's, I'm not very good at my plumb line, but imagine that straight down in this particular case, and this one's half the distance down. Now, when I look at that triangle, this line, it actually doesn't matter which way it goes, but it's easy to see if it's straight down the inclination line. If that line is straight down, if this is 1,000, it's upside down to you. That's 0, it's not to me. But I should be, to get to the 500 position along this line, I have to come halfway up, right? But since it's just a line and it's linear, that is truly halfway. Right? Doesn't matter what, as long as it's not vertical, it's going to be halfway along that particular line. And it could be at any angle, actually. It could be way over like that. And it'd still be the same thing. If that was 0 and that was 1,000, it would still be halfway across the line to find the point that was at the same elevation, right?
So if this was at 800, you just put 10 tick marks in.
Right, yeah, let me get to that. But here's what's the point of that? If I have, so I got a high point and a low point, and I got another intermediate point. If I want to find the point that's halfway between the two, I just measure halfway down.
Mm-hmm.
Make sense?
Mm-hmm.
So it's halfway to there because I've gone through half that distance. Well, that turns out well, if you think about that for a moment, that proportion is always preserved in the sense that if you have an arbitrary distance, so that, let's see if I can make this one, I'll write on here now, I'll make this one 1,000 and make this one still 0. See if I can make this about right. Call that like 400 or something. Mm-hmm. Right? Now I could redraw that triangle. See if I could draw the one I just drew, something like it. It looks about right. That's 0, that's 1,000, this is 400. To find the point on this line that's this same height, all I have to do is set up a proportion. If this length is L, and that's just, I take my ruler and physically measure if it's with a map, or if it's physical distance, if I have a tape, or you have a GPS position here, GPS position there, same difference. Just know the distance. There's some distance between them. It can be map scale, it can be, just as long as you know this distance, there is a proportion here such that this difference in elevation, so 400 is to the total distance, 1,000. That proportion is an unknown distance that I want to know, x, is to L. Does that make sense? When my numerical example here where it was half, I was halfway there, so it's 500 over 1,000, so 1/2. 1/2 of L is x is half the distance. Here I'm 40% of the way, so it's 0.4 times L gives you, or will give you that distance. Make sense? It's a simple proportion. What that means is really easy. You just find, you measure over here for 0.4, get that distance, 0.4 over, there's your equivalent elevation to that, and you've got strike line. The only cautionary note here is watch out that you get your direction right. High to low, or low to, the distance from low to high and low to intermediate, or you have to go the other way, high to intermediate. Just make sure you use the correct starting point on the proportion. This always confuses people. The best way to do this is to do it, okay? And you got a problem here, you get to do this. The first part of the assignment is just to use the field data and other things that you had, but see if you can do this with the calculations that are in here. The other thing you can do, that the last point I'm going to extend here, is you can, once you know, I should add this part, once you know the strike, you can also determine the dip, right? By knowing these positions. How would you do that? Once I know this, how am I going to figure out the dip? Correct. But what's the definition of dip? This is a strike line, right? Which is a structure contour line equal elevation. What's the definition of dip?
Perpendicular to the strike line
The strike, the inclination, right?
of the horizontal plane.
So if I add to this diagram, a line, we can use another color.
It's the angle.
Perpendicular line.
Okay.
That is a dip line. So if I go from the strike line, directly down dip, I can also extend this position parallel to strike. Once I know strike, correct? Taking that distance, now I need the real distance on the ground. It's the horizontal distance, the map distance, between this position and that position. And I also have a fall. Rise over run. Say again?
What's the question?
What's rise over run?
Slope, yeah.
Or what's the trig function? You've got, there's a change in elevation, which is that number minus that one. And you've got a distance, which I can get from the map across that. I have to convert map distance to real distance. How do I do that?
Scale.
Scale, the map scale. So I have, so say what I have here, 400 feet or 400 feet for the other example. There's a change in elevation. I'll make up a number. Say that's 642 feet. Pull the number out of here. But you can determine that amount. What's that theta?
That's the dip.
That's the dip.
Yeah.
So how are you going to get theta?
You're going to do the measurements.
Where am I going to get it? Watch, it's a simple calculation. Opposite
rise
over adjacent,
yeah.
rise over run.
400 over 642, so that's 16.
42 equals what? That's tangent. So the angle whose tangent is that, gives you the dip.
Huh.
Simple trig. That's the simplest trig you'll do here. But you're done, right? Now you got strike and dip from 3 arbitrary points. And you can also turn that around. When you get once you get strike and dip, you can also do an alternative calculation. If I wanted, now the next thing I might want to do, which is the last part of your assignment, would be, okay, why don't I turn this around another way? Maybe I should wait for this and have you do this part first. But then I don't have to keep talking. If you know that this number is like 40 degrees, right? I want to know what's my map distance might be for me to change elevation along the inclined plane, or the structure contour change, the change is, say, 100 feet. In your maps, that's one heavy contour interval, the bold contour interval, because it's a 20-foot contour. If I know that amount, how am I going to get map distance? I want to know what this distance is. But I know it dips 40 degrees.
Did Jason ever have hypotenuse?
It's exact same calculation, but now you don't need to do inverse, right? Opposite over, call this x, 100 over
Okay.
x equals tangent 40.
Gotcha.
So 100 over tangent, actually, I guess I should have done it the other way around because it would have been cotangent. But got the idea? You can calculate x now from that relationship. Once you know x, you can also make lines, equal space lines, that are structure contours. So this is 400, 300, 200, such. So you can turn it around and you can figure out where something should be. And one part of your assignments, it shows you that you can actually predict where outcrops should be by doing that. And we'll lead you through that a little bit more when we get to that. So dive into the assignment. I did a lot to you real fast. The best thing to do is just do it rather than listen to me talk.